Humanity faces an energy crisis. The huge technological advances that took place in the last century and are still happening today have created an energy-driven society, a society whose lifestyle demands a constant flux of electrical power and fuel. Therefore, it's of the utmost importance the development of a sustainable and non-pollutant source of energy to satisfy society's demands while ensuring environmental protection. Fusion power presents itself as a possible solution. It's the process that powers the Sun, happening deep inside its core. It consists in combining two lighter atomic nuclei to form a heavier nucleus, releasing energy. A possible approach to achieve the high energy state required for such reaction is through magnetic confinement of plasma. But what is plasma? Plasma is sometimes called a fourth state of matter, and it's obtained by adding energy to a gas so that some of its electrons leave its atoms. This creates a soup of negatively charged electrons and positively charged ions, plasma. Such process happens, for example, when a lightning strikes and ionizes the atmospheric constituents. Given that the individual elements composing plasma have electric charge, they can be pulled together or pushed apart by electric and magnetic fields, which grants plasma a very interesting behavior. To achieve fusion, plasma should be confined at extremely high densities and temperatures for long periods of time. The most well-developed approach to magnetically confine plasma with these properties is through the use of tokamaks, donut-shaped devices that use a powerful magnetic field to confine hot plasma revolving in its interior. However, this presents complex technological challenges, and no reactor has yet been able to confine plasma with these properties during the time required for industrial application, mostly due to instabilities and various transport phenomena. Therefore, it's critical to develop diagnostic methods that enable an accurate description of the plasma behavior and conditions inside the reactor. These methods should ultimately allow for real-time position control of the plasma, which requires high-speed processing. One of the strongest candidates to fulfill these requirements is tomography. Tomography consists in the reconstruction of an object's 2D cross-section from the acquisition of several of its projections. Let's see an example. Imagine 4 squares emitting light with different unknown emissivities, and we can only measure the power corresponding to the projections of these emissions. So, if we use 4 detectors, we can measure emissivity 1 plus emissivity 3, 2 plus 4, 1 plus 2 and 3 plus 4, which correspond to 4 lines of sight. We get 4 equations and 4 variables, which means we can solve the system and reconstruct the emissivity profile. Plasma tomography functions just like this. We have detectors placed around a specific cross-section of the tokamak, each one corresponding to a specific line of sight, and from their measurements, we have to reconstruct the plasma profile. However, in reality, we have infinite profile points, and each point of our emissivity profile can have a different emissivity value. To make the problem even harder, the number of available lines of sight is due to technical constraints very limited. This means that we lose information about the profile, and to make up for this loss, we need to use certain assumptions. This creates a problem because for certain regimes or profile areas, these assumptions won't be correct, and the final reconstruction will contain artifacts and incorrect emissivity values. In my master thesis, entitled ISTTOK Tomography with Machine Learning, I will be working on the tomography system of IST tokamak, ISTTOK. My first step will consist in studying the behavior of electromagnetic radiation inside the ISTTOK vessel, including detectors viewing geometries and the effects of reflections on the vessel walls. The required data will be collected through the use of a cylindrical gas discharge lamp placed at various positions inside the tokamak vessel. To better understand radiation behavior, I will simulate the system using ray tracing techniques. These results will be compared with experimental data in order to tune the simulation's parameters. Then, the collected data will be used to train a neural network which will enable fast profile reconstructions free of artifacts usually caused by other methods. Finally, the tuned simulation will be used to generate high-resolution data by virtually placing the lamp in hundreds of possible positions and simulating power received by each detector. As done before, this data will be used to train a new neural network that should outperform the previous one. This work will be performed at IPFN under the supervision of Professor Horácio Fernandes and Professor Diogo Ferreira.